And so finally, lately we've been working with Franco to try to answer that question here, or at least partially answer that question, which is kind of a big question in the, at least in the mass flow community, is to how to correctly evaluate the performance of volcanic mass flow models used for hazard assessment. So as we know, it's pretty tricky because it could be easy that somebody that doesn't really know how a model should be used can take a model and then run some simulations with some random input parameters and ended up with an output that can be shared during a volcanic crisis and could end up being very confusing with for people and stakeholders. So I think I can show here a few examples of some steps to follow to avoid such situation, but I think there's not one single way of doing it. But at least the way we propose it is to start with some detailed field investigation of the flows or the deposits. So, of course, if most of the cases you cannot go in the field, so you're gonna have to rely on some satellite imagery, and that's fine. You can do a lot with that, just looking at satellite images. But first thing you need to do, especially for volcanic mass flows, is to try to map the flows and the deposits to try to estimate the volume, for example, or the area covered using some thicknesses of the deposits. And then you can go a little bit further and also do some sedimentology to try to get more idea about what are the grain size distribution of your deposits, and what is the volume of each of the units if there's several events that occur during a single eruption, which is the case most of the time. And once you do that, then you should end up with a list of key flow metrics that you're going to use for your simulation and your modeling. So these should be the source conditions, the types of flows, the inundation areas, the volumes, the runout distance, some mobility parameters like the H/L ratio, for example, and some impacts parameters that could be useful, like some ideas of dynamic pressure. So for most of the case, you cannot get all this, right? But if you can get some of these, that's super useful, because then you can better constrain the inputs of your model, and that's what you want to do, right? So something we're still trying to do, at least in the PDC community, is to disseminate these metrics once we have them. So you basically publish a paper, right, about these particular flows or deposits, and then one step that people tend to forget to do is to try to integrate them into a database. For example, we have the FlowDat database developed by Sarah Ogburn, and that regroup a lot of input parameters that are super useful for model calibration, model input calibration, that we tend to forget. So that's, I think, one crucial step would be to get a better a database of these flows and deposits. So there's some recent initiatives that have been done by several people in the flow community to try to develop more comprehensive databases for flow parameters. Once you've done that, then you can try to integrate this data into some numerical simulations of volcanic flows using various models. So that is basically trying to do some inverse modeling, right, for model validation. And I think that's a step that any modeler should do before trying to move to the next step, which would be the forecast modeling or the forward modeling. First, you need to make sure, as I said at the beginning, that your model is able to reproduce what you want to reproduce. So using past case studies, using laboratory experiments, using observational data is super useful to try to reproduce what happened in the past and to make sure your model is able to do that. And then once you've done that, then you can move into the sensitivity of some numerical or statistical model to some of these key input parameters, and then you can use probabilistic and forward modeling. But I know sometimes some modelers tend to forget the second step here and move directly from the observation to the probabilistic or forward modeling, which could be problematic because then you don't actually validate your model. You're not making sure that your model can actually do what you claim it can do. So all this is to try to reduce model uncertainties and establish a consensual validation procedure for volcanic flow models. And so finally, these are the validation metrics we've been developing back, I think it was back in 2010 and 11 with Jacob Richardson and Chuck, to try to validate models, mostly flow models. So this is based on the fact that when you're comparing the footprint or the area inundated by an observed flow to a simulated flow, you can either by differentiating different things. So for example, here you have a circle that represents the area of your simulated flow, and you have another circle representing the area of your observed flow. And the intersection between the two circles is going to give you what we call the true positive. So that would be the area that is inundated by both your simulated flow and your observed flow. Then you will have an area that is only inundated by the simulated flow, but not the observed flow. That's what we call the false positives. And then you will have an area that is inundated by the observed flow, but not by the simulated flow. And that's what we call the false negative. And then you have the true negative, which is areas that are neither inundated by both, but in our case here, we're not using them because we think it's an infinite area. It can be anything outside of the inundation area of both flows. And so you can develop different metrics, which will be like some coefficients that can be expressed as a percentage. So for example, you have the first one that is called the Jacquard similarity coefficient, that is one of the most used metric, that is using the true positives and the union of the area inundated by the observed and the simulated flow. So in that case, you're dividing your true positive by the sum of the true positive plus the false negative plus the false positive. So it's a pretty restrictive coefficient that's going to take into account everything that the flow is able to simulate or everything that the flow is not able to simulate. Then you have another one, which is a model sensitivity that is only going to take into account the false positive. So this time you're forgetting about the false negative, and you're dividing your true positive by the sum of the true positive plus the false positive. And then finally, you have the model precision, which is going to only take into account the false negative. So forget about the false positives, and you divide your true positive by the true positive plus the false negative. So by using these three different metrics, you can basically evaluate any flow model from some observational data, and try to figure out if your model is producing mostly false positive or mostly false negative. So if the model is conservative or not, compared to a particular case study. So one of the first model we use and case study we use with Chuck was the Panabas Lajas in Guatemala, in the Atitlan caldera, that occurred in 2005, October 2005, after the tropical storm Stan that destroyed the village of Panabas. And we ended up by comparing different things there, mostly the flow thicknesses, velocities, and then we also run some simulation with a model called Flow2D to end up with some validation matrix and Bayesian matrix that I mentioned before. And what we ended up finding is that we had a calibrated model and an uncalibrated model, which was based on the rheology of the model, and we got better performance with a calibrated model with fewer false positive and false negative. But also, we found out that both the calibrated and uncalibrated models have higher sensitivities and precision, which means that they have more false positives than false negative. And that's, in a way, that's what you want, right? You want your model to actually go further than the observational data, rather than omitting some of the inundation area. So in a way, this was conservative, what we call conservative models. And then I also did some evaluation of depth average models at Merapi, and these are some of the comparison here between Titan 2D and VoltFlow using the 2006 block and hash flows at Merapi. So the first case study was like just a small runout, single pulse PDC with no overbank. And these are the results at the bottom for the 3 different metrics: Jacker, fit, sensitivity, and precision. So you can see that in that case, Voltflow was doing a slightly better job than Titan 2D with a higher Jacker fit and then lower sensitivity but higher precision. And then the other case study was a long run out multiple pulse PDC events with some overbanks. And in that case, actually Titan 2D was doing a better job, higher Jacker fits than Voltflow, with some higher sensitivity and model precision as well. So this is just an example of how we can compare different models using these metrics and a single and a particular case study at a particular volcano. So I'm going to stop here, and then if you have any questions, I can answer them. Otherwise, we're going to move to the script that Franco wrote to actually do what I just showed you there directly on Victor using any map that you have, any inundation map, and any model.
Hey, Sylvain, can I ask you a question?
Yeah.
If you go back to, I think it's your slide 15.
Yeah.
Which shows the. So what's interesting to me is I mean, I think all these metrics are fine, and certainly the Shikard index does its job, which is sort of like to look at the total overlap. So I mean, obviously, if TP is filling all the circles, basically, then you've got 100%. And usually we see it doesn't. But one of the things that occurs to me is when we apply this stuff to hazard, not all pixels are created equal, right? So maybe if you're mostly interested in the model performance in a certain area, like in the area of the alluvial fan at Panaba, where the village was, would there be a way to modify these models to say pay more attention to the important part of the flow?
That's a super good question, and that's exactly what we're trying to find out right now with Franco. So that would be the next steps.
Oh, okay.
Is to develop a Jacker fit that would be like a probability Jacker fit. So basically by trying to set up some weight on the pixels based on how far away they are from the observed flow boundary, for example. So developing like a function, like when you're far away, you put more weight because that's a like higher error for your model that is close to the flow boundary. Or like you said, like if there's some area of interest that you wanna look at, then just like take that particular area and develop a Jacker fit that's gonna calculate the metrics only for that particular area. Something we could also develop is something where you have not only one run, but you have an ensemble of simulations, and you gonna develop a Jacquard fit that's gonna be based on the number of hits per pixel.
Mm-hmm. Mm-hmm.
And so trying,
That's a really cool idea.
Trying to evaluate like a probabilistic simulation output rather than just a deterministic one. So there's some work that have been done by Stuart Mead and others where they try to develop this I don't know how they call it, like it's not a threshold but like a buffer for the
Oh
Jacquard.
God, yeah. I
But it
remember
was
that
really
paper.
obscure to
That's
me. I
really
mean,
subjective.
yeah.
I found it really subjective.
Yeah, I read the paper several times and I didn't really understand exactly how they were setting up this buffer, and it looked a little bit obscure to me. So, but that's basically, one way forward. And I think there's several ways of
Yeah.
improving these metrics, and depending on the use you wanna how you wanna use them. Yep.
Mm-hmm. Mm-hmm. Yeah. Also, it seems to me that when it's very clear when you have a flow actually occur in nature, and then you run out a bunch of models and try to simulate that flow. But for everything, I mean, lava flows and pyroclastic flows, we've pretty small data sets for that. It's like, oh, it fit that PDC, but it didn't fit that PDC. But there aren't like 100 of them. We can compare models to. I don't know. It seems like it would be interesting to compare like just many models among themselves using the Jacquard index or some derivative of the Jacquard index. So have you guys done that?
Well, I mean, for the moment, there's, like I was saying, there's no that, like you were mentioning, there's no really database of, like, where you can
Yeah.
like just grab like inundation area and maps of previous flows, and so
Mm-hmm.
I mean, for the moment, what you have to do, like, to dig into the literature, find the paper, and then trying somehow to digitize the map, and trying to then run your model. And then of course you don't have the good DEM, right? Because it's a DEM from you will need a DEM from 20 years ago that didn't exist. So you're
Oh,
gonna run
right,
that
right.
you're gonna run that on the current DEM, and of course you're gonna get different results, right? And so
Yeah.
so there's many obstacles to that. But for recent case studies, um, where the flows have been mapped well, but that's because that's also another thing, is that it really depends on how well the flow were mapped. And
Mm-hmm.
for most of them, sometimes they were just approximately drawn on a piece of paper, and then now we have satellite images that are all georeferenced, and so we can do a much better job of outlining the inundation area. So I think for recent case study, we have the tools to actually build databases and compare many models to this case study. So I think it will be just a job of like identifying probably a range of case studies that goes from like a small volume dense PDC all the way to a large Ingham-Brights, and then trying to run models on these different case studies, and calculate these validation metrics and the Jacquard fit on each of them, and trying to end it up with some kind of common database and for the benchmark of these models. That would be super cool.
Yeah. 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 The version control also becomes really important, right? Because like, with molasses, I know that molasses was compared to the Tolbachik 2012 flow, and that was pretty cool and successful. But now since then we've modified molasses.
Yeah,
So,
yeah, sure.
I mean, it's like
No, that
really hard
depends.
to
Yeah, when you
compare.
have different version of the code, then that would be, and that would be a thing, something that needs to be done, not just once, but each
Yeah.
time you create a new version of the code, then you should run it again and calculate the Jacquard again to see how much that changed compared to your previous
Mm-hmm.
version. So that's, yeah, something good. Or if you have a new DEM, or if you have something that changed compared to the first time you were running the simulation, then I think you should do that process again. So I think having a cyber infrastructure like Victor to actually be able to go back and run the same exercise, but then just changing one or two things in there, and I think that makes sense, and that could really open the benchmarking exercises to some new users in the community.
Yeah. Super cool.
Yep.
Anybody else have questions for Sylvain before Franco gets started? Cool. Franco, are you ready?
Can I hear you?
Can you hear me now?
Yes.
Okay, excellent. Good. Nice palm trees on your last slide, by the way, with the question slide. I haven't seen that the USF palm trees
Oh, yeah.
being showcased there. Nice. All right. So let me share my screen. Yes. Okay, window.
Just while you're going there, did you guys get your script loaded up into the shared drive, or did that?
It was not working still.